so my studies of galaxies really took a sharp turn in the early 1990s when I took this image. It's not a single image, it's a digital panorama. It's the first digital panorama of the Andromeda Galaxy. So my students and I put this together, but I took these images in the early 1990s from a telescope in Arizona. And it's the same image, seen 4 times over, at different contrast levels. This is our neighboring galaxy, the Andromeda Galaxy. You don't see the panorama. Each image is made up of 57 digital images stitched together. Images in blue light, images in infrared light, stitched together with the right contrast level, different contrast levels for the 4 images. Here's a different image of Andromeda taken by an amateur astronomer. And what I do nowadays for my research is use the Keck telescope in Mauna Kea to study the details of Andromeda and other galaxies like it. You'll see the Keck telescope coming into view. This is a very powerful telescope. The Keck telescope mirror is 10 meters across. So if you tried to place this on the stage, it would overhang the front. It would barely fit between the 2 curtains. That's the mirror of the Keck telescope. It's very expensive, so we've carefully put it on top of a volcano in Hawaii, on top of Mauna Kea. And I use this telescope to study the details of the Andromeda Galaxy. And one of the things we discovered, my students and I discovered this in 2005, 13 years ago. February 2005, we put out a press release saying, wait a minute, the Andromeda Galaxy is 5 times bigger than people have thought or assumed for the last 100 years. So instead of being 100,000 light years across, we found stars all around Andromeda that are moving like the Andromeda Galaxy, that have the right properties to be at the distance of Andromeda. So Andromeda extends out to 500,000 light years, not 100,000 light years. Okay, so this was an important moment in my research to make that discovery. So, what is special about 500,000? There's nothing special about 500,000 light years. Andromeda is probably even bigger than that. So 500,000 is 500,000. Okay. Andromeda itself is 2.5 million light years away. People have now found the Milky Way galaxy is comparably big. What this means is our galaxy and Andromeda are not quite the island universes that Kant thought they were. There's not that much space between us. The sizes of these galaxies, if something is 500,000 light years in diameter, and it's only 2.5 million light years away, it's only 5 times further away than its size. So there's not a lot of empty space between galaxies. And that's only how far out we've mapped it. It actually goes beyond that. There's no reason to believe it ends right there. Every evidence suggests it goes beyond that. So if that is true, if galaxies do have relatively little empty space between them, galaxy encounters should be quite common. Galaxy collision should be quite common. And so that's what brings us to the next slide. And the problem with a galaxy collision is it takes a long time. A galaxy collision happens over a few billion years. So no astronomer has lived long enough to watch a single pair of galaxies collide. What we do instead, we can still study them. And I'll show you how we study them. Here's a computer simulation of what happens when galaxies collide. So what we can do is take these 2 galaxies on a computer simulation. As they're coming together, we pause our computer simulation, and here are 2 real galaxies that are about to collide. Okay? We now go back to our computer simulation, and you see that soon the 2 computerized galaxies are starting to actually overlap. One is going through the other. And at that point, we again stop our computer simulation right there. We change our perspective, and we can find around us that there's 2 other galaxies, the 2 real galaxies, that are in the process of passing through each other. So it's not the same as the first 2, different pair. And now we go back to our computer simulation, the 2 galaxies are stretching each other out. Stop the computer simulation, these are 2 real galaxies that are stretching each other out. We go back to our computer simulation, the 2 central pieces start to fall back together. And before they completely collide, and before their central black holes collide, we stop the computer simulation, change our perspective, and stop. Here is a real pair of galaxies going to the collision. You've seen 4 different pairs now, not the same pair. We go back to our computer simulation, the central parts now merge, And as they merge, we stop our computer simulation, change our perspective, and here's the final pair of real galaxies, right there, going through a collision. So galaxies take 5-7 billion years to collide, but the wonderful thing is there are many of them around, and we could take snapshots of different colliding galaxies at different stages of the process. The best analogy I can think of is imagine you have a weekend homework project where you want to study the effect, or you're asked to study the effects of human aging. Human aging, what does that do to human beings? You have the weekend to study it. Human beings don't age very much over a weekend. So what you can do though, is you can collect information from human beings of different ages, who are at different stages of the aging process, and you can use these snapshots in human life to stitch together what happens when a human being ages. As they grow older, their height, their weight goes up, the amount of hair on their head goes up initially, then goes down, and so on. Hair color changes. You can construct all of these things without watching this happen in any one individual. That's the point. That's exactly what happened in that video. You saw different galaxies, different galaxy pairs actually, different stages of the process. Now, galaxy collisions are spectacular, and you might think, okay, that's all great. It's going to happen to other galaxies. We are comfortably removed from this phenomenon. That's not true. So I'm going to talk about how we are going to be part of a collision in just a minute. It comes back to our favorite galaxy, the Andromeda Galaxy. We are going to be colliding with the Andromeda Galaxy. I hate to break this to you, but this is something that's going to happen, and we'll talk about that in just a minute. So this is the Andromeda Galaxy. Again, Robert Gendler is the image of it. This white outline is an area in which we've now obtained another digital mosaic, a digital panorama. This time not using 57 images in 2 filters, not in blue and infrared. This time they're using 3,000 images taken with the Hubble Space Telescope in 6 filters, 2 ultraviolet, 2 visible light, 2 infrared. And what I'm going to do is show you a little zoom of what that Hubble data looks like. So here we go. That's the Andromeda Galaxy. This little speck is the Andromeda Galaxy. That's the Milky Way, the band of gas and dust and stars. That's the Milky Way. As we zoom into Andromeda, fasten your seatbelts because we're really going to zoom in very quickly. This galaxy is 2.5 million light years away. That's why it looks so small and insignificant. But as we zoom in using the Hubble telescope, this is what we see. This is a real image. This is part of our digital panorama taken with the Hubble telescope. You can see groups of stars, clusters of stars. You can see individual stars of different colors, like we saw in the Milky Way earlier. Andromeda is just like the Milky Way. You see bands of gas and dust right there. This is a band of dust, another band of dust right there. This is a remarkable image for the following reason. We've known Andromeda for a long time as a distant collection of stars. It's like knowing a beach by taking an aerial photograph of it. Imagine you're flying into San Jose and your plane happens to fly over Capitola Beach and it does a nice bank and you happen to have a window seat, you pull out your smartphone, you take a picture of Capitola Beach below you. It looks like a galaxy, right? It's a collection of sand, just like a galaxy is a collection of stars. But now let's pretend you take your smartphone image and you start zooming in and zooming in and zooming in, and let's pretend your smartphone is good enough that you can see the individual grains of sand. That's what this image is. You can see the entire galaxy with enough precision to see the individual stars that make it up. So we've used this. I use this a lot for my research. I'm part of a big group that uses this for our research. And using Hubble images, not this particular image that you're seeing here, but using other Hubble images of Andromeda, one of the things we measured in 2012 now, 6 years ago, is we measured exactly how fast Andromeda was moving in all 3 dimensions. We've known one component of its motion. If you've taken a physics class, you know that the motion of any particle is a vector. It's 3 components, x, y, and z. So we've known the z component for a long time. This is the motion of Andromeda towards us. We never knew the x and y components. In 2012, we measured the x and y components with great precision using the Hubble telescope. And you can imagine if the x and y components are very large, even though the Z component may be towards us, so the X and Y components are large, Andromeda Galaxy is headed in a different direction, not towards us, that we are glancing below if there's anything at all. And what we found, to our horror, is the X and Y components of the Andromeda Galaxy are practically zero. It's coming for us, is what we found. As they say, Andromeda, and astronomers wondered why Andromeda was getting bigger and bigger, and then it hit us. So I'm going to show you a little animation of what the Andromeda Milky Way collision is expected to look like going into the future. This is today. There's Andromeda, a little speck, and because we know it's coming towards us, we can predict what it will look like as we go into the future. So a couple billion years from now, Andromeda will be bigger. We have to just figure out how to live that long. If we do, we'll see spectacular fireworks in the sky. But notice the time scale, 4 billion years, 5, 7, we'll get up to 7 soon. Those two pieces will finally collide to produce a galaxy, a single galaxy, where there have been two before. Galaxy cannibalism will be part of it. Andromeda and Milky Way will produce one galaxy. We have a name for it already, Milkomeda. Have a name, Milky Way and Andromeda. Like I said, this is bad news, right? Bad news. I'm really sorry if I'm the first one breaking this to you. I notice nobody is panicking and running from the auditorium, which is a good thing because there's no place to run, right? There's absolutely no place to hide. That's the bad news. The good news is we have a long time. 7 billion years is a long time. There are many other things that's going to kill us before that, right? Our neighbor, a neighboring country, you don't know who's going to kill you before that. If you survive for 5 billion years, if you survive disease, all the difficulties of human aging, if you manage to survive all that, our sun is going to bloat up into a red giant, and the sun will hit the sky, not like a big pizza pie, and it won't be amore. It will engulf us, it will scorch us, and neither of those two things is a good outcome. Right? So we'll have to make our way to the outer part of the solar system to survive the sun. But if we manage to do all that, and I know we will, we meaning future generations will manage to do that. We'll manage to get out of escape our planet so we can survive the bloating up of the sun in 5 billion years. Then we can see these galactic fireworks. We won't have 4th of July anymore. We won't need it because we'll have it permanently on the sky all the time. Now, there's one very odd thing about this movie, the 7 billion year old movie that you may have noticed. The hills are made up of some really hard stuff because they haven't weathered in 7 billion years. All right, so coming to the next part of our journey, I'll make this part really brief. There's something very special that's happened in the last few years. Astronomers and physicists have been very excited about this, not just astronomers and physicists. People all around the world have been excited. Their world has quite literally been shaken by the discovery of gravity waves. Okay? Gravity waves are produced by merging black holes. One of the things that can produce gravity waves. You see a schematic of a pair of merging black holes. This was detected in 2015, in August 2015, and it's really changed our way of looking at the universe. The analogy, this is my second analogy, I gave you one already. My analogy is this. What this man is to sports, gravity waves are to science. Stephen Curry represents a level of precision, artistry, hard work, and enjoyment of the game that has rarely been seen before. People who never watched basketball, people who never watched sports, have started watching because of one person's achievements. In the same way, people who never cared about science, physics, or astronomy have started asking, what are these gravity waves? So I think it's a really important moment in human history that this kind of way of sensing the universe is new. I'll say a few words about that. This is a schematic of the apparatus used to detect these gravity waves. What you have on the left is a laser that shines, gets powered up by this apparatus, goes through a 45-degree piece of glass that's semi-reflective. So some of it bounces and goes up there, some of it goes right on through. And the distance between this and this, the distance of these two arms of the L are each 4 kilometers. And using this laser apparatus, you can measure at every instant whether the two arms of the L are exactly equal in length or not. And if a gravity wave comes through, what happens is the relative length of these two arms changes, very subtly, but it changes. Changes by an amount that's much less than a wavelength of the laser beam, but it's enough, sensitive enough to measure. In fact, here is the actual chirp signal, or here's the actual apparatus first, seen from the air. There are 2 of these pieces when the first detection was made. This one is in Hanford, Washington. The other one is in Livingston, Louisiana. So 2 parts of the continent received the same thing. So, you might wonder, there are many things that cause oscillations. You can have an earthquake in a neighboring state, but that earthquake might be felt by the Washington one, if it's in a neighboring state of Washington, but won't be picked up in Louisiana, and vice versa. So, by having 2 of these, even though the signal is very subtle, you can look for things that have exactly the same pattern, received at both places, nearly simultaneously, not exactly simultaneously, but nearly simultaneously. And what was received at each location was this signal over here. You can see this is from Hanford, Washington. This one is from Livingston, Louisiana. What you're seeing on the y-axis is a measure of the difference in length between the 2 arms divided by the length. So it's called strain, which is delta, the change in length, delta L, divided by L. And notice the numbers are very small. The strain is in units of 10 to the negative 21. 10 to the negative 21. It's a very small strain. But what is remarkable about this oscillation of space itself, what is remarkable is you notice how the amplitude goes up, but the frequency also goes up, meaning the waves get closer together. This is exactly what you would predict if you have a pair of black holes merging. The amplitude goes up because the black holes approach each other as they spin, they in-spiral as they spin together. They in-spiral because they're losing energy through gravity waves. They in-spiral, and when they finally merge, there's a ringing down at the end. This is the exact pattern expected from merging black holes, and it doesn't take any imagination to see that this looks like this. Moreover, this looks like what was received in Louisiana, except it was received a few milliseconds later. Why was it received a few milliseconds later? Because the pair of merging black holes, if it was over there, this is Washington, that's Louisiana, would have been received at Washington before it reached Louisiana. It's traveling at the speed of light. But you can measure the difference in time. In fact, that difference in time tells you where it's coming from. We're directly overhead. If it were along the bisector between the 2 locations, they would have been received simultaneously. So, this chirp heard around the world is really the first time we are feeling the vibrations of the universe. It's remarkably subtle. Here's how subtle. What does 10 to the negative 21 mean? It means the length of that 4-kilometer arm changed by an amount that's equal to 100 the diameter of a proton. Not the diameter of an atom, the diameter of a proton. The distance between Earth and Alpha Centauri changed, went through an oscillation. The amplitude of the oscillation was the width of a human hair. So I think it's a remarkable feat of engineering to be able to measure this. Yet another important thing happened last year. And a few of these chirps have been heard at this point. They've all been due to merging black holes. You can tell from the pattern it's a merging black hole. But a new kind of chirp was heard last year. And this time people said, wait a minute, these are not merging black holes, they're merging neutron stars. These are dead stars that merge. And when merging neutron stars finally smash together, you expect to get an explosion. And indeed, this spot of light had not existed before this chirp was received. And they saw the chirp, they knew the rough direction, they pointed to this galaxy, and they saw that spot of light. This image was taken by one of my colleagues, Ryan Foley, the University of California, Santa Cruz. So now the accompanying light, the burst of energy across the electromagnetic spectrum and gamma rays and light was detected with this. So What this makes me think of is the following. Astronomy has been like a journey through a beautiful but silent forest. Like all of the human species have been walking through this really beautiful forest, all kinds of sights. There's beautiful birds and flowers and animals, and we can see them, and they're mostly static, but occasionally something will move. Just like in astronomy, occasionally a star will explode or a meteor will shoot across the sky. For the most part, it's still, but completely silent. It's silent not because there's no sound, it's silent because our ears are not good enough. But in 2015, after decades of effort, billions of dollars, we had an assisted learning device that these human beings could put on, and they heard a chirp. They turned around to look, but they recognized the chirp had come from black holes, so when they turned around to look, there was nothing to be seen. The first few chirps went by that way, and then when the chirp was heard last year, it had a different ring to it, quite literally. It had the ringtone of a pair of merging neutron stars, and this time when they turned to look, they saw the bird fly away that had produced the chirp. So it's a remarkable moment in human history because we can now sense the universe in a second way through these vibrations, and we can actually connect our seeing, which we've done for ages, our visual senses, to our hearing senses. We can connect those two to the same event. It's a really important moment in astronomy. Now, the person who predicted gravity waves was Albert Einstein. That picture was taken in 1912. The picture on the left is Albert Einstein. 1912 was when general relativity was published, and it predicted that there should be gravity waves. And this time we saw gravity waves from merging black holes. The first person to work out Einstein's equations exactly was this person, a gentleman named Carl Schwarzschild. He worked out Einstein's equations exactly and showed that you can have these things called black holes whose gravity is strong enough to trap light. So, it's these two people whose work has finally been verified 100 years later. What is special about Carl Schwarzschild is he did all this work when he was in his 20s and 30s. 20s and 30s, no pressure for the college students here, no pressure. Carl Schwarzschild died in World War I. He died in 1918. He was fighting for Germany. This was a Jewish family. This is before the rise of the Nazi movement in Germany. Carl Schwarzschild gave his life for his country. His son was 6 years old at the time, and one of the frequent visitors to their home was Albert Einstein. Where's his son, by the way? Martin Schwarzschild. He didn't look like this when he was born, but this is, he looked like this when I knew him. Martin Schwarzschild was a professor in Princeton. He was a retired professor in Princeton, one of my mentors. So, Einstein visited their home after his father's death, visited his mom, visited him. He is my 1 degree of separation from Albert Einstein. I'm your 2nd degree of separation from Albert Einstein. All right, so they showed the existence of black holes, and we've been talking about black holes and dark matter. I want to present 2 more things of black holes and dark matter. First, dark matter. Here is a collection of galaxies whose dark matter has caused the light of background galaxies to be distorted in a way that Einstein predicted. Einstein predicted that light should be bent. What you're seeing here, this blue image, that blue image, and that blue image, are images of the same galaxy. We're seeing a mirage due to the bending of light by the collection of yellow galaxies in the picture. The blue galaxy is further away. As the light comes through, it gets bent in different ways by the bending effects of mass. And this is something Einstein predicted also. Here's another spectacular example, the smiley face lens, where the same galaxy's light has been stretched out like this, another galaxy's light has been stretched out like that. And of course, they predicted the existence of black holes, and that's what brings us to Stephen Hawking. Hawking predicted that near the event horizon of a black hole, there should be the production of matter and antimatter particles, and occasionally one of those will get trapped by the black hole, the other one will escape. That's the essence of how Hawking radiation works. Like I say, I have the good fortune of listening to him speak in person, and he is already being missed by the science community. So to wrap up my story, I want to go back to galaxies and talk about the origin of galaxies. What you're seeing here is a map of the sky in millimeter wave radiation. This radiation is the afterglow from the Big Bang. This radiation is coming to us from when the universe was only 380,000 years old. Today it's 14 billion years old. We can see this afterglow from the Big Bang. You notice it's not perfectly smooth. There are bright spots and dark spots. The bright spots are in red, dark spots are in blue or black. Those are tiny fluctuations at the level of 1 part in 100,000. Those are seeded by quantum mechanics, essentially related to the uncertainty principle. But over time, these fluctuations get blown out by gravity, first by inflation and then by gravity, into galaxies. So gravity causes matter to congeal. So these tiny fluctuations existed because of quantum mechanics shortly after the Big Bang. Inflation is a very rapid period of expansion where these get frozen into the fabric of the universe and stretched out, and then gravity takes over and turns them into galaxies. Let's see how that happens. In this computer simulation, you'll see these tiny fluctuations early in the universe's history. 0.08 giga-years is 0.08 billion years. But over time, gravity causes the rich to get richer and the poor to get poorer, and that's how galaxies are formed. And again, this is a computer simulation in which many billions of years are being compressed into a few seconds. It's a very high-speed version of the universe, but a computer simulation of the universe. And 500 kiloparsecs over there, 500 kiloparsecs is about 1.5 million light years. Just that little bar is 1.5 million light years. That's roughly the distance between us and Andromeda. Us and Andromeda, we're 2.5 million light years apart. So you can see these beautiful filaments. This so-called cosmic web is much bigger than the World Wide Web, much bigger. And along these filaments, in this other simulation, you can see galaxies come together and form. And you'll see that galaxy collisions happen in these computer simulations, and we've seen that in nature, these same sorts of galaxy collisions are going on all the time. So I'll let this movie run just a little bit longer. You see one galaxy forming there. It looks like a beautiful spiral galaxy. Here's another beautiful spiral galaxy, till this one smashes into this, like the Milky Way Andromeda collision, and then neither will look like a beautiful spiral galaxy after the collision. They'll look like an elliptical galaxy after that. See, they get tangled up, the disks are destroyed, but over time, another disk forms, and so on. And these beautiful computer simulations have also enhanced our understanding of the universe. So to wrap things up, here's a map again of the afterglow from the Big Bang. If we zoom in on one of the hot spots, one of these hot spots gave rise to an infant galaxy, multiple pieces. These pieces came together because of gravity to form a mature galaxy. Within it, there are stars, some of which underwent explosions. In these explosions, there were wonderful elements in the periodic table that got incorporated into the next generation of stars and planets, causing them to form complex molecules and wonderful living things. Thank you. We have time for a few questions, please. Okay, so we have a microphone here and a microphone here. I'm going to run this like a competition. We're going to ask one side first, then the other side, but we're going to give people a few minutes to leave. This is your time to escape the Milky Way Andromeda collision if you want to get away. But otherwise, if you are interested in asking a question, please come up to one of the microphones. I'm going to go back and forth, and this is going to be a little competition to see if the left side can ask better questions than the right side. I'm just kidding. Let's give it just another minute, please, while people are making their way out, and then we can. Over. All right. We can't hear you, so let's make sure the microphone's working. Maybe they need to turn it on that way. Oh, Puragra? All right.
So we're part of stardust. When we die, we release those elements into our galaxy and continue on.
Mm-hmm. No, that's absolutely right. We are We were born out of dust, and that dust is certainly going to return to the earth, unless there's a medical miracle that keeps us going, right? But at least as far as we know, that's exactly right. We are part of that cycle. We're absolutely a part of that cycle.
Okay. My question is about gravity waves, at least my first one. Are gravity waves the same thing as electromagnetic? Are they electromagnetic radiation, just extremely fine? If not, how are they different?
Oh, sure. That's a very good question, and in fact, the first comment was an excellent comment too. So, gravity waves are different from electromagnetic radiation. Gravity waves are literally oscillations in the fabric of space and time. Let me distinguish between those two things. They can both, there's some similarities. They both travel at the speed of light, 300,000 kilometers per second. They both travel through vacuum. They don't need a medium to travel. Sound requires a medium, but electromagnetic waves and gravity waves don't require a medium. Those are two things they have in common. An electromagnetic wave, as the name suggests, is an oscillation of an electric field and a magnetic field. It's an alternating oscillation of an electric and magnetic field. That's what all electromagnetic waves are. Whether we're talking about gamma rays, X-rays, all the way to radio waves, these different electromagnetic forms of electromagnetic radiation have different oscillation frequencies and different lengths covered in a single oscillation. It's as though, think of electromagnetic radiation as a bunch of people who all run at the same speed. Some have very short strides, they take many strides a second. Some have very long strides, they take very few strides per second. The very short stride, many strides per second are gamma rays. The very few strides per second, very long strides are radio waves. So electromagnetic radiation is electric and magnetic field oscillating. We've known about this in waveform at least for a long time, going back to Maxwell. We knew about light, ray optics, geometric optics from Newton and even earlier. Gravity waves, the understanding of that came in 1912 or shortly thereafter, came with general relativity. Here's what a gravity wave is. I'm going to try and explain this. So, general relativity, Einstein tells us, don't think about gravity as a force, think of it as a distortion of space-time due to the presence of some mass. What do you mean by distortion of space-time? The Earth's mass causes space and time around it to be distorted. What distorted space-time means to me is the following. If the Earth weren't there, light traveling from point A to point B would go in a straight line. That would be its natural path. Light always takes the path that takes the shortest amount of time. And that would be a straight line if there's no mass present. When there's mass present, general relativity teaches us that the straight line path grazing the surface of the Earth actually takes longer than taking a curved path. So the shorter path in distance takes longer in time. So light follows the shortest time path, which is a curved path. So the presence of mass can bend space and time in this way. So if you have a black hole, it bends time around it. If you have a pair of black holes, you have a complicated distortion of space and time. If they're now orbiting each other, then that distortion is constantly changing, and that generates gravity waves that carry away energy, causing these black holes to inspark because of the loss of energy. That's what a gravity wave is. It's an oscillation in the fabric of space and time itself. Everything that's embedded in space and time, which is literally everything, goes through the same oscillations when a gravity wave goes by.
I'm curious about the spinning.
For galaxies?
For everything, the planets in orbit, the galaxies, the suns. Was there just, when the Big Bang occurred, did it just set everything in a spin?
Not exactly. You guys are asking tremendous questions, all of you. So let me describe the spin. The best analogy, I'll give you two analogies to discuss the spin. The spinning of galaxies is related to the flattened shape, the disk shape. You know, when the man in the pizza kitchen, the woman in the pizza kitchen wants to make that pizza dough, they spin it up in the air and it forms this flattened structure. The question is, what causes that spin? So we can see that the flattened structure of galaxies is related to spin. Why is it spinning? When it's not seated at the Big Bang, actually, it's not. So at the Big Bang, you have these fluctuations, these clouds of gas and dust are collapsing under gravity. If it were a perfectly radial collapse, there'd be no spin. It'd just be an infall. But these things are not happening in isolation. This collapsing cloud has other clouds passing by. So if there's one passing by in this way, it might give it a torque in this way. But then this one may give it a torque in the opposite sense. The net effect of all these torques will not be zero in general. Every one of these is feeling torques from neighboring things. But it could be a very slight torque. Why are they spinning so fast? They're spinning fast because this slight torque gets built up to a very high speed when gravity causes it to contract. In the same way that an ice skater, he or she puts out their arms, when they go into a spin and they want to spin up, they bring their arms in. Or a diver who wants to tumble rapidly goes into a tub. So there's something called conservation of angular momentum, where the radius multiplied by the spin, that product is conserved. So when the radius shrinks, the spin rate goes up. So that's why you see so much spin in the universe, because gravity is so, these torques are everywhere, and gravity is causing things to shrink everywhere. That combination is what produces the spin.
So does that mean then that all the spins can be totally different directions?
Exactly. Different galaxies have different spins because each one was born out of a cloud that had its own set of initial influences. Note, the planets, on the other hand, were born out of a single rotating nebula or rotating cloud, so they all share the same spin. So the planets in the solar system have the same, not just the same orbit around the sun, but the same sense of spin. But different galaxies, especially that were born in different locations, won't care, each one won't care about the other one's spin.
So when they collide,
there's a general cancellation of spin. That's why you get non-spinning galaxies like elliptical galaxies.
Thank you.
Sure.
So I've read a lot of science magazine stuff, and nobody's ever explained where water comes from. Has this been formed in the gaseous nebulas, or what?
Water molecules are formed in a couple of different ways. They are formed in gaseous nebulae. They actually also formed in the outskirts of stars. You see all kinds of cool things out there in interstellar clouds. Water is certainly seen, OH is seen, ozone, O3 is seen, methane, all kinds of things are seen. In fact, C2H5OH has been found in nebulae. C2H5OH is very familiar to the college students in the crowd. It's alcohol. They found the bar at the center of our galaxy. No, different kind of bar. But no, these molecules are actually produced quite commonly. We tend to think of water associated with life, but water is everywhere. Water is everywhere, quite literally everywhere, including places where it's certainly too hot to sustain life as we know it.
Okay, thank you.
Sure.
In the near future, we'll have a new tool available in the form of the James Webb Space Telescope.
That's correct.
Which I understand extends our vision into further range of infrared light that we currently cannot see with the Hubble.
Mm-hmm.
What kinds of expectations would you have as far as possible discoveries using this new tool?
That's a very good question. You know, the James Webb Telescope, exactly as you said, is going to see further into the infrared. It will let us see galaxies that are further away. Because of the expansion of the universe, the light of galaxies is redshifted to longer and longer wavelengths the further away they are. So it will allow us to see more distant galaxies. It will allow us to see with greater sharpness than even Hubble, because it's a bigger telescope. Its infrared capabilities, as you say, will be dramatic. Some of its capabilities will be also in the optical, but just better than Hubble, more powerful, sharper vision than Hubble. But the extension to the infrared will be a truly new capability compared to what Hubble has. So more distant galaxies, looking further back in time in the universe's history, that's what more distant means, because the further away a galaxy, the longer light is taken to reach us. So looking further back in time, being able to see more details inside these nebulae, because the infrared light is not blocked by dust as much as optical light. It would be tremendous for studies like of the stellar populations in nearby galaxies. You saw the detail of Hubble, this will have even greater detail. So more detail gets you a lot of information. The launch of this James Webb Space Telescope was supposed to take place in October of this year. I was part of 6 different teams that were writing proposals. The deadline was April 6th, the deadline for proposals, and it got postponed. The deadline of proposals got postponed because launch has been postponed until 2020 now for James Webb.
Thank you very much.
Sure.
you mentioned briefly about dark matter and its importance in the formation of complex molecules and life in galaxies. And I guess my question is, I have a really loose grasp of the term antimatter, and I'm wondering if that's related to dark matter.
That's a good question. Antimatter is real, but it's not related to dark matter. Dark matters, we know more about antimatter than we do about dark matter. Antimatter, every particle we know of, electron, proton, neutrino, neutron, every particle we know of has an antimatter counterpart. These are produced regularly in laboratories. They're produced in high energy experiments all the time. We understand antimatter very well. We do know that the kind of flavor that exists in the universe is of one kind. We call that matter. The antimatter particles are fleeting because every time they encounter a corresponding matter particle, they annihilate and produce energy. Dark matter is much less understood at the present time. We know how much there is. We know now that it's made up of tiny particles. It's not made up of dead stars. They're called WIMPs, weakly interacting massive particles, because there was a theory called machos that didn't survive. There's a massive compact halo object that's been ruled out. So we know sort of what kind of particles they're made of, but we don't know their microscopic nature in the way we do for antimatter. Okay. So two different things. And when dark matter is discovered, we'll probably find out whether dark matter is its own antimatter particle, whether they can annihilate. And there's a theory at least that has that as a possibility.
Thank you.
Sure.